And there we are.
Okay.
There we
So
go. Gary, how you doing?
I'm doing fine.
Yeah, um, our loyal fan base, all five of them, they've been asking me where is the good intelligenic Mr. James? And so I told him I will connect with you and bring you, get you back on the
All
air here.
right.
So
Well, promise fulfilled.
there we go. Anyway, so now, like I say, our loyal fan base, all five of them can see the good intelligenic Mr. James. Okay. Anyway, what I wanted to, in the vein of historic electronic devices, I wanted to talk about some weird ones that I did actually have some experience with back in the day. But what got it started was the genesis, the idea for this was I was talking to my daughter, Natalie, a few months ago, and we noticed that this little electric toy, a photoelectric toy, actually exhibited weird behavior that looked like negative resistance. And we thought, that's what got me thinking about it. Okay. So
Okay.
I put together a presentation of, let's see, share screen. And okay, and this is probably not in the right place. So let me go back up to the top. So, and let's start this little slideshow. This has to do with negative resistance and historic electronic devices. And anyway, let's go. So, okay, so I called this Going Negative Part 1, Historic Perspectives on the Weird Phenomenon of Negative Resistance, because there is a Part 2. In Part 2, I was going to show how you could use negative resistance to analyze sinusoidal oscillator circuits. You remember the Colpitts oscillator?
Yes.
Yeah. You remember how when we were just getting into amateur radio, how we memorized those circuit diagrams of Colpitts oscillators and Clapp
Exactly.
oscillators and Hartley oscillators, and we had no idea how they worked. But
Yeah.
we memorized the diagrams in case on the license exams they put one up and said, "What is this?" You remember those?
Exactly. Yes, I do. Yes, I do.
Okay.
Very well.
I was going to try to explain a little of how those things work. That's part 2, though.
Oh, okay.
Let's
Sounds good.
roll on here. But before we do that, I just want to mention that shortly in the past, on the 23rd of December of 2022, was the 75th anniversary of the transistor. That was the day that John Bardeen and Walter Brattain and William Shockley demonstrated the first transistor to their colleagues at Bell Labs. And it's probably the most consequential invention of the 20th century. I would argue that it has had more wide-ranging effects than just about anything that humanity has invented. And the IEEE says that the field effect transistor is now the device that, or the man-made object of which humanity has made the most in its entire history. Supposedly there exist more field effect transistors today than there are letters printed in all the books that have been printed since the invention of movable type.
That is quite a statistic.
Well, and I imagine it's true considering, hundreds of millions of transistors in one microprocessor chip. And
Yeah, exactly.
Okay, so anyway, do you remember ever hearing about these things called tunnel diodes?
Yes, vaguely. Didn't understand much of what they were, but yeah, it was one of those obscure developments in the electronic components.
Yeah. Well, I remember hearing about them when I was a kid, and I was like you. I was, boy, that is weird. How does that thing work? It was an idea that whose time kind of came and went. You don't hear about them much anymore. So, but
Mhm.
unfortunately, my collection of old electronics, I don't have any of these things.
Mhm.
But I found a photograph of a General Electric 1N3716 tunnel diode. And just for comparison, this thing here is a 2.54 or tenth of an inch millimeter, 2.54 millimeter or tenth of an inch jumper. It fits
Mm.
on adjacent pins on an IC socket. Just for comparison, so this thing is less than a tenth of an inch long. This thing's tiny.
Mhm.
And the tunnel diode had this really bizarre current versus voltage characteristic. And I appreciate the graphics that you did here, where it had three distinct regions of operation at low voltages, typically up to about 100 millivolts or so. The current would rise with increasing voltage. And the conduction mechanism was a quantum mechanical tunneling effect, and that's where the diode got its name. But you get past about maybe 100 millivolts or so, and that starts to taper off. And then at around 300 millivolts or so, you start to see ordinary diode conduction take over. And that gave rise to this kind of N-shaped current versus voltage curve. And
Okay.
in its region one, the slope of current versus voltage is positive, and it's positive in region three, but in region two, it's negative. The change in
Mhm.
current with respect to the change in voltage across the diode is negative. And in that region two, that's what they call negative differential conductivity, or more commonly, it's called negative resistance.
Okay.
Okay, so
Which is the topic of our
yeah, the tunnel
session today.
diode shows negative resistance. And here I found an image of a 10 milliampere germanium tunnel diode that was measured on a Tektronix curve tracer. So these are actual measurements of a live device. And you can see this is 50 millivolts per division. So this one peaks at around 70 millivolts or so. And a little over 300 millivolts, you see the diode conduction begin, but you can definitely see the N-shaped
Yes.
IV characteristic. So, well, my own this is where I actually had a connection to the tunnel diode. You remember our days at the University of Illinois?
Oh,
Remember them
yes.
well. Okay.
Yes, we do.
Well, I'm curious, what were you taking in the spring of 73? What classes were you doing? Do you remember?
Spring of 73, I
Junior
was
year.
taking uh, design, I'm sure, graphic design, studio versions, and learning about photography, graphic type stuff. 3D construction, sculptures, that kind of thing. And they even dabbled into a little bit of what they call stone lithography, which was an ancient printing technique on a actual stone. So yeah, I was doing some different things back then.
Yeah, well, at that same time, I was taking a class that was called EE 344. That was called Theory and Fabrication of Solid State Devices.
Mm-hmm.
And this is the silicon wafer I was working on. You've seen this, I've shown this to you.
Yes.
And this little chunk of silicon has working transistors, bipolar transistors, and MOS capacitors on it. But one of the projects we did that semester, we made with a crude fabrication rig, we made little germanium tunnel diodes. And if I remember right, I think my peak to valley current ratio was like 3-to-1. It actually worked. And the
Okay.
professor who taught this class was none other than Ben Streetman, who was the author of this textbook. Starting in about, I think it was the 5th edition here, the name Sanjay Banerjee was on it as well. But this is one of the classic texts in solid state
Mm-hmm.
electronics. And that class EE 344 was the only class I ever took, only electrical engineering class I ever took, where we had to wear goggles and acid-proof aprons in the laboratory, because we were handling some nasty stuff like hydrofluoric acid and phosphoric acid. And
yes.
yeah. But anyway, so that's where I had a personal encounter with the tunnel diode. Okay, so let's take a quick look at this circuit. We have a battery and the tunnel diode and a resistor in between. And if you write an equation for the current as a function of the diode voltage, you see that the battery voltage minus the voltage across the diode divided by the resistance is the current that's flowing through the resistor. And this graph is just it's just a graphical solution of that equation. And it reaches its, if the diode voltage were 0, you get the current, the battery voltage divided by R. And if the diode voltage goes to the battery voltage, then the current goes to 0. Because if the voltage here and the voltage here are equal, there's no potential across the resistor. And the slope of this line is -1 over the resistance. Okay. And this is known as a load line. And all possible combinations of diode voltage and current have to fall on this line. But now if I superimpose on top of that the IV characteristic of the diode, the diode voltage and current at which this circuit operates can be found by finding the intersections of the load line with the IV characteristic of the diode.
Okay.
So this is a graphical way of simultaneously solving equations, one for the load line and the other for the diode itself. Okay. Classic technique.
Yeah.
Okay. And in points 1 and 3, this is, you have a stable operation, but in point 2, that's unstable. It would be like, you know, if you had a couple of valleys, shall we say, and a hill in between, you put a rock on in the little valleys, it's stable, stays put. You put one at the top of the hill, and if you disturb it just a little, it rolls down one side or the other, you know, balanced on the knife edge in point 2.
Yeah.
Okay, so this led to combinations of voltage and current permitted by the load line and the diode characteristics. Yeah, forgot my own. I forgot what captions were in my own slides. So this led to an interesting application of the tunnel diode, or a proposed application, to use it as a logic element. So let's suppose the battery voltage is here at voltage 2. And you see the load line intersects the IV curve at 3 places, 2 of them stable, 2 and 4, and 1 unstable at 3. Now, let's say that it's operating at this point, and then let's pulse the battery voltage up to voltage 3. Well, that has only one intersection with the diode's IV characteristic. So while the voltage is pulsed, it's operating here at this combination of diode voltage and diode current. Then if you drop the battery voltage back to 2, it comes to this stable operating point.
Okay.
So it previously was here. Now after the pulse, it's here.
Okay.
Or if it's operating here at 4, and if I drop the battery voltage from 2 to 1, it's got this
intersection
stable operating point. But then when the pulse goes, the negative going pulse from 2 to 1 goes back to 2, it comes to this operating point and stays there. So in other words, by pulsing the battery voltage, I can shift the operating point to a new stable location. I have one of 2 choices, and it acts like I can represent 0 and 1 in digital logic with those 2 different operating points.
Those 2 points.
Yeah, so you could make the tunnel diode as act like a flip-flop.
Okay.
And so there was thought like, we can make memory elements, you know, or use flip-flops in digital logic circuits make them with tunnel diodes, but advances in transistor design overtook the tunnel diodes. So this idea never really came to fruition. But this bistable behavior is an interesting facet of negative resistance. Okay, now,
yeah, okay.
But it actually, believe it or not, negative resistance actually had its origins back in vacuum tube days. You remember?
Really?
Go ahead.
No, I was going to say that's an interesting observation.
Well, you probably don't. Yeah, this is probably not really something you need to review, but I threw it in here anyway. You remember the Fleming valve, as they called it, which was just a diode
Yes.
vacuum tube. It had the plate and a hot cathode sealed inside a vacuum. You remember?
Yes.
Only conducts in one direction. And in 1906, Lee DeForest added a wire spiral that he called the grid to the diode or two-element vacuum tube to produce what he called the audion. And a change in the voltage between the grid and the cathode could cause a corresponding change in the plate current.
Yes, kind of like a tap on a water faucet.
Yep.
You control the flow.
Yep. And this phenomenon of being able to change the plate current with the grid to cathode voltage, known as transconductance, it made amplification possible, and modern electronics, as we know it, all comes from or was made possible by that. Like long distance telephone calls and radio, vastly improved radio circuits, all of that made possible by amplification. It was called the triode, but it had a problem that capacitance between the grid and the plate would seriously limit the high frequency response of the tube. And it was due to a phenomenon called the Miller effect, which we talk about in the junior year of the electrical engineering curriculum. And so a second grid was added between the plate and the control and the grid to act as an electrostatic screen. And so the new grid got the name screen grid, and the original grid was renamed control grid to distinguish the two. And this 4-element tube, plate, screen, control grid, and cathode, was called a tetrode. So, and the tetrode had vastly improved high frequency performance over the triode, but then it introduced its own unique problem. And these are the plate characteristics of a type 24 tetrode. I would imagine these were from the 1930s. And on this graph, each of these curves represents plate current versus plate voltage, plate current on the y-axis, plate current on the x-axis. And there are curves for control grid voltages from 0 volts up here to -6 volts in increments of -1.5 volts. And the plate voltage goes from 0 to 500 volts. The screen grid voltage was constant at 90 volts. And they also included a graph of screen current on the same set of axes. That's this one with the blue arrows. But notice here, there's this region where you see this. As the plate voltage increases, the plate current is actually decreasing. That
similar
is
to the graph of the tunnel diode that we started with.
Yeah, you see, there's that kind of N-shaped characteristic of negative resistance. Well, so what? Well, actually, what caused it was kind of interesting. When you accelerate electrons from the cathode towards the plate and they smash into the plate, if they arrive with sufficient kinetic energy, they can dislodge electrons from the plate itself. And if the screen is at a higher voltage, these electrons can actually flow from the plate to the screen. And the net result is the greater kinetic energy that electron has when it hits the plate, the more secondary electrons it generates, the lower the plate current goes. Well, again, kind of so what? Well, but before I begin on to that, it was enough of a problem that the vacuum tube designers added a third grid, which was called the suppressor grid, between the plate and the screen, and its job was to repel secondary emission electrons back toward the plate. And this, with the addition of the suppressor grid, this now became the pentode. And the suppressor grid was operated at a much lower potential than the plate or the screen, typically ground, and sometimes pentodes were made with an internal connection between the suppressor and the cathode. You remember seeing those?
Okay. Yeah.
Our old friend, the 6AU6.
Yeah. Very common.
Pentode. Okay. And these are the the plate characteristics of a 6J6 pentode, and you can see that the negative resistance region, let's see, this one was operating with a screen voltage of 100 volts. Plate voltage falls below 100, and you don't see the N shape, characteristic of negative resistance.
Okay.
So the pentode solved the problem, but well, what's the problem if the resistance goes negative? Well, let's take a look at a simple circuit model, and again, thank you for the graphics, of a tetrode RF amplifier. So you have a tuned circuit to select the operating frequency. We have a load resistance that the amplifier is driving, and the tube itself is represented by a voltage-controlled current source in parallel with a resistance, the so-called plate resistance. The plate resistance is the reciprocal of the change in plate current with respect to plate to cathode voltage. And if the tube's operating in its negative resistance region, the plate resistance is actually negative. Okay. Well, again, so what? Okay, I just said what it's at the bottom of the screen. Okay, so, and again, this is your graphic. Remember, we have a capacitor here, and what we're going to do is we're going to switch it to the battery to charge the capacitor. So it's got some stored energy, and then at time t equals 0, we'll flip the switch and put this charged capacitor with stored energy on this inductor and parallel resistance branch, and we'll see how the voltage across the three elements behaves with respect to time after closing the switch. Okay. And I'm not going to work through the derivation of this. I did this so that you don't have to. But the voltage that appears, this is after time t equals 0. The voltage that appears across the switch is given by this expression. I'll work through it in a moment here. I'll explain it. It consists of an envelope, which has got an exponential term, and a second term, the product of the envelope with a constant amplitude sinusoid term. Or you can rewrite this to get rid of this cosine and sine combination. You can write that with just using the cosine. You can combine this to form that expression. Those two are equivalent. Again, I did the math. You don't have to. The letter zeta represents the damping ratio, which is 1/2R times the square root of L over C. And the undamped natural frequency, 1 over the square root of LC. You've probably seen that before. Formulas you've memorized and so forth. And this phi is the phase angle in this expression. Okay. But the thing to take away from this is you have an envelope multiplied by a sinusoid. Now, caveat, this is for a damping ratio of less than 1. Damping ratio greater than 1, you don't get this oscillatory behavior, but we're not interested in that case. So, I did a simulation of a 1 farad capacitor charged to 1 volt with a 2 ohm resistor and a 1 Henry inductor. And simulation with simulation software, multi-sim from National Instruments, produced that light blue curve. But I checked my calculations against that, and those are the red dots inside the blue curve, and you see they match. And I've shown here, this is the decay of the exponential envelope. So you see how this exponentially decaying envelope, the sinusoid fits inside of it?
Yes.
You've seen this before. And this particular circuit has an undamped natural frequency of 1 radian per second and a damping ratio of 0.25. If I increase the resistor, the damping ratio goes down and you see it rings longer. Now, let's go back to this. What happens if R is an open circuit? If R is infinite? That makes a damping ratio of 0, which makes this envelope constant, and you get a constant amplitude sinusoid out of it.
Mm.
Okay, so it just rings
All right.
forever.
Yes.
Now, that also means that you're not extracting any energy from it, because if you were extracting energy, it would start to decay. But
Correct.
okay, but if that resistance goes to 0, we've got a constant amplitude sinusoid. Now, what if we have a negative R? That produces a negative damping ratio, and a negative damping ratio makes this a positive exponential. You see what's happening there? You get an exponentially diverging envelope. This has got a damping ratio of minus 0.05. Okay, so keep this in mind. Let's go back to the tetrode RF amplifier. Here we have the plate resistance in parallel with the load resistance. If the tube is in its negative resistance region, this R sub P will actually be negative. But if the parallel combination of these two resistors is infinite, that is, the negative resistance and the positive resistance in parallel look like an open circuit, then I have an LC circuit with a load resistance of 0, no damping, and I have a constant amplitude oscillator. And if the overall resistance is negative, then I have an oscillator whose amplitude will grow exponentially until, it can't do that in a closed system. It's going to reach some limit, but so if the plate resistance combined with the load resistance is infinite or negative, you got a circuit that will oscillate on its own. And if what you want is an RF amplifier, that's a terrible thing to have happen. It goes unstable and takes off oscillating on its own.
Yeah.
Okay, so that's the problem. Okay, so, but in some circumstances, we can exploit that. So let's take that tunnel diode and let's use a battery to bias it to operate in its negative resistance region. And this choke is essentially a large inductance. At DC, it's a short circuit, so the battery voltage appears across the tunnel diode, but for high frequencies, it looks like an open circuit, so the battery disappears from the circuit at radio frequencies, and the DC block capacitor, goes away, becomes a short circuit at high frequencies. And if the tunnel diode's operating its negative resistance region, this circuit forms a self-sustaining oscillator. You just put DC on the tunnel diode and away it goes. Magic.
Yeah.
It's so-called negative resistance oscillator. Now, what happens as the amplitude of the oscillation builds, the diode voltage begins to make excursions out of its negative resistance region into its positive resistance regions. And that's what the mechanism that limits the amplitude that this thing can produce. It will self-limit in that regard.
Okay.
So there's no violation of, well, it continues to diverge forever till it sucks up all the energy in the universe.
Yeah, exactly. Yeah.
But anyway, but this was a circuit that I saw in some magazine or publications when I was a kid. Somebody had built an amateur radio transmitter using a tunnel diode and a resonant circuit and connected up to an antenna and actually was making contacts with it I was just fascinated by
Very
something. This
interesting.
little thing could actually function as a transmitter.
Yeah,
Okay, so
incredible.
now here's where I actually did work with negative resistance devices. This device over here that you see, that is a Doppler radar velocity sensor that operated at 24 gigahertz. And the source of microwaves was this thing, this Doppler radar transceiver. It had in it what was known as a Gunn diode, which was connected to pin 1, and there was a choke here in series with pin 1, and a Schottky barrier mixer diode to produce the difference between the transmitted signal and its Doppler shifted return. And that difference frequency was the Doppler frequency. You count that frequency to know how fast you were moving.
Okay.
Okay. Same thing they do in those radar velocity guns you see at the ballparks. This is not the exact transceiver we use, but it's very similar to it.
Okay.
Anyway, I spent about 3 years working with this thing. I was not part of the design group, but I was in charge of the group that took the thing from prototype phase to volume production. And anyway, but you bias the Gunn diode in the middle of its negative resistance region. It has a quantum conduction effect, negative resistance effect that happens in N-type gallium arsenide. We bias it in the middle of its negative resistance region, put it in this resonant circuit, which the the resonant cavity acts like an LC circuit, 24 gigahertz microwave source.
Okay.
So anyway, that's part 1, a little background on negative resistance. And part 2, when we get it done, will be about using negative resistance to explain how those oscillator circuits that we studied back in our formative years when we were learning about amateur radio, how those things work.
Okay, very good. Well, look forward to part 2 and completing the story. That was quite interesting, and several aspects that were very informative, especially about the tunnel diode, which I was not totally familiar with, but now I have some understanding of what that device was.
Okay, well, all righty. So look forward to seeing you in part 2, and I'll show you how we can explain the Colpitts oscillator and the Wien-Bridge oscillator using negative resistance. You take care, my friend. We'll see you soon.
That sounds very good. All right.
Take care.
Okay, good day.